the celebrity of DFE, I believe. But for those who is new to the DFE community, I will introduce Karon. Karon is a professor in computer science at UBC and the director of the Sensory Perception and Interaction Lab, in other words, SPIN Lab, and she's AKA being called Queen of Haptics. Before joining UBC on 2000, she got her PhD in mechanical engineering at MIT and gained professional experiences as a robotics engineer and haptic researcher in the industry. She's a leading figure in haptics and HCI research in particular. She published numerous top-tier papers, and she won numerous awards and served for a number of academic communities, including the recent one where she served as a general chair for UWIST 2020. I think the DFE community is hugely in depth to Karon for her services, for enabling, not only enabling this community, but also Karon being on one of the initial forces who made this community starting off. So, and also I want to highlight she's serving as one of the 3 co-directors of the community still, and I believe she will hold that position for at least next year, along with Lisa Hosty and Ian Mitchell, who are the other co-directors. And I believe she will guarantee a peaceful transition of power, unlike what's happening on the other side of the wall. So let's start the talk. Karon, I think Karon will talk about emotional robots and magical objects and enchant us with her magical research. Let's see.
So it looks like my screen is sharing okay, so I will take it away. Thanks so much, and thanks for the beautiful introduction. I have to say that after all this time, it's a real pleasure to be finally sharing my research with you. I've gotten so much out of learning what everyone else's research is and doing what I can to support yours. And so mine goes a little different direction, although I've worked with a lot of you over the years. So this will be fun. So I'm going to start by saying something, showing a kind of a video that I thought of this when I was last September, a little over a year ago, I was enjoying myself in Sweden at a meeting of neuroscientists who were talking about affective touch and neuroscience, and they were talking all about kind of how our neural system perceives affective touch, so emotional touch, and how it's processed in the neural system. And it occurred to me that what they were saying was very interesting. It was very new to me. There was many things I was learning, but it didn't actually align with my physical knowledge of being in the world. And I went up and dug, before I gave my keynote talk there, I dug up this video to say, look, you guys, this is what's going on. And so here we have Jocelyn. I should have asked Jocelyn for this video, actually. She probably has a better one than me. And I don't know if it works well enough over Zoom. I found the video is a little bit choppy, but what this is a little cat who's having a really, really luxurious pet. And I see Jocelyn has got the same thing going in her window over there. So you can just look at Jocelyn's cat if you want to instead. You'll get the same idea. And the thing is that what the neuroscientists were saying is that affective touch is passive. In other words, you experience it on your body. And what I want you to look at, and probably a lot of you have had experiences like this cuddling a cat just luxuriously and watching how the cat is pushing your head into your hand and you're cuddling its neck and you're responding to it. It's not the same as petting a passive stuffed animal or something. You are responding to it. It's a partnership when you're petting this cat. And you're giving the cat pleasure and the cat is giving you pleasure back, and it's very two-directional. And it's not passive. It's going both ways and you're engaged with it. And so I challenge the neuroscientists to really think about that two-way thing. And always, the bigger lesson, I guess, is to bring your own personal knowledge of the world into your research and always be double checking what you're getting. So with that introduction, and that started some really great conversations at that conference, which I'm still trying to get my head around. So this thing about people and animals, it's really started to get my attention a while back, maybe 15 years ago. And so it's a long story that I'm going to try and lead you through with a lot of facets. I like giving this talk because it brings together a number of the different things that I work on, but always kind of comes back to this theme of what the heck is going on when we touch animals. Not just animals, but I found animals a very useful package to a platform to study this idea. There's a lot, of course, emotional touch with people. We have emotional touch with objects. But when you're talking about animal touch, it's a little more studyable. It doesn't have some of the social loading that human touch does, but it's much more active and interesting and vibrant than when we touch passive objects. And so it's just fascinating to look at it. I watch people touching animals. I think a lot when I'm touching animals. And around the time that I started getting interested, this maybe in the kind of mid 2000s, I started to read all these papers and research findings about, health outcomes and how, people who had had heart attacks, when they do these massive clinical studies, they would find that outcomes were so much better if you had a cat at home. It outplayed, how sick you were, what medication you were on, what kind of intervention you had, what all your other risk factors were, was the cat was so important. I think that was an Australian study, and there was a similar thing for cancer recovery that had to do with dogs. And you're thinking, like, what is it about having a cat or a dog that is having such a profound influence on your health when you have been very ill, when you've been not just had a cold, but you've been very ill? And, is it because you're getting out for more walks? Is there more social involvement? You have responsibility to another being that you're taking care of. And all of those things may be a factor. But I also wondered, what is going on with that touch? You're actually touching, it's doing something to your brain when you touch an animal, and you activate these neuronal circuits that are your affective system. What is going on that is having some kind of a protective outcome on your body, and what is going on there, and could we study it? And so I also want to make a particular introduction. At least one person in the audience, my colleague and your colleague, Lisa Holste, will know Poppy. I had the pleasure of meeting Poppy around that time, kind of in the around 2010 probably. And Poppy is was a very talented care dog at Connect Place Children's Hospital. She was a golden retriever, but she was not any golden retriever. She was one who lived and worked at a children's hospice, and she was good at what she did. And she had a partner who was a care worker, but Poppy worked on her own a lot of the time. She would wander around Connect Place, and she knew where to go. She knew how to use her body and her senses to help other people. And she would mediate conversation. She would know to climb into someone's bed when they were particularly in need of a cuddle. And that's where you would find her, is doing her work. And then sometimes she would get tired and she would need a break, and you have to go outside. And very sadly, Poppy passed away a couple of years ago. And I should also say it was her colleague and caregiver was Hal Seiden, who is still the director of Connect Place, who actually introduced us and allowed me to go into Connect Place and shadow Poppy for some of her work in her younger days. And I was so inspired. What is Poppy doing? How does she know? How is she using her body? What is going on when she is giving so much relief to the people around her? And so it is that kind of thing that we started wondering about, and this has triggered this whole line of research. And so one of the things that I want to know is, how do you sense emotion from touch? How does Poppy know that someone is sad? Okay, and how does she know what to do with it? How does she know when it's getting better? And I could say the same thing about my own dog, or my dogs, or Jocelyn could probably say this about her cat. Is like, they're getting something, they're using lots of channels, of course. They're using the tone of your voice, the sense of your footstep on the floor and the feel in the room. There's many things that they're bringing in, but some of it they're getting out of the way you're touching them. Anyone who's a pet owner will know this. So this platform of using affective touch and human-animal interaction as a platform to study, it's less loaded. But how do people use and read touch to communicate emotion, and how do animals do it? And so the eventual goal is to allow people to interact with emotionally aware objects, and to build these objects that can actually facilitate that kind of interaction. And this work really took off. I said we were doing a fair amount of affective work, affective touch before Steve got here, but he was the one who really got me going on the animal model. And I just always have to tell the story of how I met Steve. He's from Texas, and he called me up in like 2007 or something. And I get this, you know, this heavy Texas Southern accent. He says, yeah, I was reading about your work, and I was thinking it would be really fun to come to UBC and work on this stuff because, you know, my girlfriend, she had a cat, and I really liked the cat. And then I broke up with the girlfriend, but I missed the cat, and I was really trying to remember like the cat sitting in my lap, and the cat, there was something going on there. It's like, I really want to understand that thing with the cat. And it was really like that. And I thought, you know, this guy is so crazy. You always have to have a person like that in your lab. And this was before a lot of people are doing research on animal-like robots and as a vector for affective anything. And so it did seem pretty out there and weird at the time. And you know, you need a little bit of that. So Steve came, and he embarked on this odyssey, which has really changed our work. And this is the idea, okay? This is the concept of what we started to try and pioneer. And it just has so many pieces that we have to solve in order to make it work. So imagine you have a girl named Chloe, and imagine that Chloe is looking at a bit. This is what we're calling them these days, these little robots we've made. She's looking at this object, and you're saying, I want, you know, the goal here is we want to do something that's kind of like Chloe is playing with a cat and having some of that wonderful richness that's going on there. So the first thing you actually need is, say, we want to know if we can sense Chloe's emotion through touch. How would you do that? Well, for the first you have to sense the touch. And so we can't sense the touch with the current sensors, certainly not what we had then and really barely what we have now. So we needed to invent new kinds of touch sensing and machine learning to recognize that before you could even know what's going on with the touch. The kind of touch sensors we had did not sense the stuff that we need, that people are getting when someone touches them or an animal gets it. Just wasn't perceiving it. And then you have to go inside the bit, and the bit says, what emotion is this person showing me? It's not enough that you've just figured out the features and the sensor values. You actually have to understand that touch and actually put it in some kind of context to interpret it. And so let's say the bit has some kind of a brain, some kind of a model going on inside it, and the bit can say, oh, she's angry. Now the bit has to decide how to react. How do I feel about that? So it needs some kind of an AI. It needs a personality. It needs a therapeutic agenda, perhaps, if that's what its job is. Okay. And the bit has to say, how do I feel about this touch? Okay. They have to make up their mind what their response is. And let's say in this case, the bit says, terror. I'm afraid. Like, this is not good. And then somehow the bit has to show this. They have to display it through their body using just touch. Or if I was building a robot that could do other things and other channels as well. So the bit has to physically render through their body, terrified. And this means that their body has to have the capability, the expressive dynamic range to actually convey convincing emotions. And so we set out to build very simple robots that anyone can build and teach to show believable, complex emotions. This is hard. It's completely different from the sensing side. We needed to do both of those at the same time, but they're different challenges. Okay, and then we want to know, can we change Chloe's emotion through touch? So when she touches this little creature that somehow she's scared at, can we actually have her go through an emotional transition because of this interaction and do this virtuous loop? That's the challenge. That's what we're trying to build. And look at all this technical stuff we have to do before we can actually make that work. We need to make sensing. We need to do interpretation. We need to figure out how to have some kind of a personality in this thing, a strategy. And then we need to be able to display it. We need to build these things. Maybe there's a lot of personalization going on. Maybe not all kids are like Chloe. And then we need to evaluate all of this. And so basically that's it. We've been trying to build all these pieces up for the last 15 years. And so I'm just going to show you a bit of that work. Not all, but just a general idea. So here's another picture of the same one. This picture is actually from one of Steve's early papers. It's basically the same idea. We're still hacking away at the same model. So there's the person's expression. It goes over into the robot land. The robot has to recognize it. The robot perceives an internal emotion. Somehow the robot needs to express that internal emotion. The person has to recognize it. So all this stuff on the one side, on the left side here, is happening in the person. and the stuff on the right side is happening in the robot. And of course, we can only control what's happening in the robot. And so that's where we've been focusing on our work on kind of these edges between them, but also learning how to get insight into what's going on in the person. So the robot platform allows us to study individual elements and break them down and then put them back together in some kind of a synergy. And that's really the high level approach. And so here's the first, it's really not the first version. There was a whole bunch of prototypes and puppets and all kinds of crazy things that we did before we got to this point. But this is kind of the masterpiece that Steve built for his PhD thesis, which he finished up in around 2014. And so you can see what it looks like. This was really the best we could do with the technology of the day. And it was a fiberglass shell with what we call force-sensitive resistors stuck on the outside that could pick up the force, the pressure you were applying in that particular spot. It had a jacket over it. We tried putting kind of, silicone gel and stuff to make it feel a little bit softer, but then we lost sensitivity on the sensors. They didn't work very well. And so we called this a turtle. I call a turtle wearing a fur coat. It didn't really feel very mammalian. And then we had this internal thing, and Steve had worked out through all his previous prototypes that what he really needed to render these different emotions, the breathing motion was really important. He needed some way of conveying the arousal. So the ears, he used the ears to get stiff and softened to kind of like a cat or a dog's ears perking up to show its alertness, but something really focusing on the sense of touch. So there's very little visual going on. It was really that you'd hold this thing in your lap as the size of a big heavy cat, and feel all of these things going on. It had a heart rate, did not have temperature because basically the thing is heating up so much from the motors, and then you cover it with fur that we were just always trying to cool it off. So we did not use temperature control as an explicit model. So this was a platform that we used to do a whole bunch of studies and got lots of, even with all its limitations, we got a lot of useful information out of it. So we call this the Haptic Creature 1.0. Steve's masterpiece. And he's really set out to do these three big questions. First of all, how do people interpret the creature's emotion rendering? How do people display particular emotions to the creature? And do people's emotions move when the loop is closed? And Steve didn't actually able to look at the third one, but a subsequent student, Yasmin Sefagar, who's pictured at the bottom there, was able to go after that one. I'll just say that we made a ton of progress on all three of these, enough to give me great confidence that this was promising, that this is something that we can do. The technology has to get way better, but this is the information we're looking for, and the potential with people is actually there. And so, and there's a series of landmark papers that came out of this work, which I can't go into in great detail, but I'll just give you a sense of it. This touch dictionary, which Steve compiled, is don't try and read it. I just wanted to give you a picture of kind of one of the really important artifacts that came out of this work, which was this was based on a video study because the touch sensors just weren't up to the challenge. So he videoed people touching the robot in order to express all kinds of emotions, and he cataloged everything they did with a qualitative study, and then just carefully described what these looked like and said, this is the way that people touch the robot. And we and many others refer to this touch dictionary as a pretty canonical inventory of the different ways that people touch animals for expressive intent. And so in addition, we got a bunch of frequency data about this, which I'll show in a moment. But first, I have to explain to everyone in the audience who might not know about it, the basic concepts of affective computing most commonly used in the field today is this two-dimensional model of arousal and valence, which is basically arousal is how excited you are, how much the emotion is. Is it a strong emotion? Is it a very neutral emotion? And then valence is which direction. Is it a positive direction or negative direction? And you can put you can put any emotion on this grid. It describes a lot of it, although there's a lot of overlap. There's a third dimension that's often used, which is called dominance, and that, for example, could distinguish, kind of stress versus anger, which might be both very high energy, negative valence emotions, but one is a more fearful kind of thing, more of a non-powerful versus a powerful version of those emotions. But I just want to emphasize that this is a static model of emotion. It sort of takes the idea of treating emotions as if there are static states that we just kind of get there and hold like a photograph. And I'll come back to that later. But this is the model that is generally been used. And so of course, when we were starting out that work, that's what we used as well. And so we were trying to see if we could identify, make correlations between the emotions that people are trying to represent to the robot and what their gestures were. So if you consider these touch modes as gestures, you say, is there a correlation between which emotion they're trying to convey and which gestures they're using? And if you're talking about distress, then yeah, it's pretty promising. It's like a one-to-one correlation. But if you look at aroused and then excited, to just use two other examples, is terrible. It's clear that you are never going to figure out that this robot is, that the person is aroused versus excited just by looking at which gestures they're making, because there's tons of overlap. It's not a clear identification. And so we're saying, oh, okay, so detecting the movement they're making is clearly not going to be the whole story here. That's not going to be enough. It's going to be more complicated than that. And I will just, I won't be able to go into this now. I'll just say that fast forward on that work. And really what we have found instead is that it's you can detect a lot of this, but what you're actually getting is the way that people are making these gestures, not which gesture it is, but something changes about the way they execute these gestures when their emotion changes. And so we're actually looking at a much more subtle thing, things like the speed and the pressure they're using and the forcefulness with which the abruptness with which they're making the gestures. Those are the things that are really the cues, not the gestures themselves. And so just to move on, this was Yasmin Sefagar, and she was a master's student who overlapped with Steve towards the end, and she took on the challenge of actually seeing if the robot, this robot that Steve had built, could change people's emotional states. And what she found, she did a controlled lab study with normal people, or intending to do it with kids, but we found it was very difficult to actually run this study on kids, particularly kids with anxiety disorders. They would not follow instructions or sit still, or it was just terrible to run a lab study on them. And so we backed off and tried to develop our protocol with university students, thinking that we would not get any signal here. We did not expect this intervention to make any difference whatsoever with them. We were just trying to pilot a protocol. To our surprise, we found quite strong results. And basically what this study looked like was, if you're holding this robot in your lap, just like Yasmin is modeling there, all fitted out with physiological sensors, very unnatural, not a realistic environment at all. And the robot is breathing, it's making its breathing motion. We had centered in on breathing as being super important. Or it's sitting still, it's just sitting there, nothing going on, versus you're holding just a cuddly, an object that is not our robot, but is about the same size and weight and texture. That you see a big difference in the calming effect it has. So all your physiological and self-report metrics actually moved in a direction to show a decrease in anxiety state if the robot was breathing versus any of the other conditions. And this was an unexpected result that we were not looking for in young adults, because we thought it was way too silly for that. I'm seriously, a robot is just kind of going up and down a little bit and that's going to calm you down. But it did. And so that's what we realized, that there was a much stronger effect going on here than we had realized. And so feeling breathing, this and other things that we've done, other studies have really honed in that feeling breathing is a visceral cue that impacts anxiety markers. Why? What's going on? And so I will just take an aside here. As we were doing all this work, the news about the creature got out, and lots of people would come into the lab and they would see and they would visit, and they were just, and constantly we're getting these stories of, you know, my kid is autistic and I'm sure that this would help them. There's anxiety disorders. Please, could you actually do something therapeutic with this robot? It's what we need. And while there was other robot work going on, none of them were actually focusing on the sense of touch as a modality that was a powerful one. And we were doing these rigorous scientific studies with it. and that had really been our goal, is just to understand what was going on. But now, oh, well, actually, you know, deploying it in a health setting, that's kind of that's kind of interesting. And so we tried to look at that and say how you would do that. But the problem was that the robot we had was completely unsuited for that. And so it's what we had built was something that was capable of doing state rendering. So it could display these different emotional states. It was able to actually render convincingly in ways that people could agree on. Oh, it's sad, it's happy, it's glad to see me, you know. But it couldn't do motion transitions. It couldn't do very much. It was just this proof of concept for a stuffed animal, basically, to be able to render emotions in a convincing way. So we needed to build a different robot. And so I got a big whack of money to build this thing. And I thought, this time I'm not going to ask a poor computer science PhD student to actually do a big engineering project. We're going to go to the pros, and we're going to have a real design firm help us build our next robot. And I spent a lot of money on that and a lot of time. And we decided we actually need something to do interaction design with, a robot that was able to do an orienting response, to do that kind of yoga thing, a downward dog. So they kind of go very cringy, tight, all locked up, huddled, and then open and expansive to sort of convey I'm happy and confident versus I'm shrinking away and scared of you. Our other robot could not do this, a robot that could kind of lean its head in towards you, so that we could actually construct narratives, that we could do smooth, dynamic things with the robot instead of just kind of flash these snapshots of a particular emotion. And so in trying to explain what we want, you can imagine how well this went. I am an engineer and I have built robots, so I understand about engineering specifications, but I had hoped with the right kind of firm, we could actually kind of work with them and develop the ideas that we want. And what we actually built was, it was kind of cute, as you can see, especially when you put the right fur jacket on it, and it kind of had this spine thing and these ribs, and it worked differently, and it could move its head. It met all our engineering specifications. It was a complete disaster. We never used it in a single experiment, and it broke all the time too. We brought it home and re-engineered it, but it still wasn't very reliable. And the problem was really that designing this weird thing of expressivity requires a lot of iteration. And this design firm just told us we had one pass through the design phase and no iteration. Our you know, multiple hundreds of thousands of dollars was not enough to get us more than one iteration on this design. And it just wasn't, it was too complex what we were trying to do. It needed more than one iteration. We need physical editing methods. And so this brought on this whole other line of research. And this is the work of Paul Bucci, who many of you know. And I love this video. Oops, I went past it instead of playing it. But this was his master's research. Why won't you let me hit the play button? There. So this is Paul's master's research, where he, this is the video for a Chi paper on Cuttlebit design, and it's really showing a completely opposite version of design to what that design firm did with us. And this is where Paul started. He started by actually making very simple prototypes that were really trying to get at a single archetypical motion that would solve all the problems we had. And we weren't trying to do multi-degree of freedom. We're just looking at the breathing. So we took 1 degree of freedom at a time and said, can we come up with a mechanism that is doesn't require a lot of power? This was a problem, was getting powerful motors that push against your hand. Instead, he has a very small, cheap motor that pulls against a spring, so that you can actually step on it or throw against the wall. It won't break. It doesn't generate a lot of force, but can move quite quickly because it's pulling against a sprung spring. And then Paul generated kind of 2 different basic ways of doing this. One of making that flexure. Here's one approach, which you have some kind of flexible thing. It could be plastic or paper or cardboard or something. And another one that is more covered with the wood one, and they have a very different feel on the outside. But then when you cover them in fur, you can see that they're actually, this breathing parameter is extremely expressive. You can change so many things about the gasping and the frequency and the abruptness of it. And the whole point is to be able to iterate these things super fast so that, and customize them. So we've had these workshops where kids have made cuddle bits, their own cuddle bits in a little bit of time. And this idea of design patterns, that you have a basic prototypical thing that you can then change and quickly run through some kind of a rapid prototyping system. In this case, it might be a laser cutter to actually cut out pieces of wood and assemble them, or something that you can cut out with scissors on the zap sheets. But the whole point is kind of coming up with a really good basic idea and then being able to quickly iterate on it. And so we have these two design systems we call them the rib bits and the flexi bits, and made these templates that you could explore the design variations. And so this was Paul's master's work that he had started on, which is really beautiful work. And the question is, how do you program these things? So now we've built them, but I've said they're so expressive, but how do you make them? It's not just running a sine wave through them. It's very hard to program. How do you actually tell the thing what you want it to do? And so this was a big challenge, and we tried a lot of different things. And I just wanted to show one of them, which is one of my absolute favorite ones. This is the work, well, a bunch of people worked on this, but it was David Marino, as a COGS undergrad, who was kind of the leader on this project.
We present Voodle, vocal doodling for effective robot interaction. When describing something abstract like motion, many people may find themselves at a loss for words and may opt to use non-word vocalizations to express themselves. Voodle translates the properties of your voice into motion on a 1 degree of freedom robot. Voodle detects features like pitch and amplitude and interprets them according to a set of user-definable parameters. With Voodle, users can quickly and naturally sketch effective behaviors in a unique conversational design space.
I hope that came across. The video has a little bit of a lag in it. So we could say, how expressive was Voodle? I'm gonna have to go through this pretty quickly. What we actually did was we brought in voice actors to co-design this with us, people who were comfortable. I can tell after demonstrating Voodle at a couple of conferences myself, that you can separate the world into the people who are willing to bark at a robot and those who are not willing to talk to a robot to try and make it expressive. And so we wanted people who are pretty uninhibited about it and used to using their voice in creative ways. And we went through this process where 3 cycles of participatory design with 3 different voice designers. And these little drawings here is that affect grid thing again. And what we had them do, you could see the session 1 is here, the column on the left, is ask them to say how well they thought they could access the space, the design space that they were trying to seek in this affective grid, given the Voodle version that they were using at that time. And then we would listen to what they said, and David would go back and revise the tool to make it more expressive, give it more capabilities, and on until eventually they felt like they had a pretty competent tool that they could really use. And so this is just one pathway. We tried lots of other things too. I just wanted to give you an example of, some of the challenges that were here and kind of the approaches we had to actually take to solve them. And so I'm going to skip this one because I'm running behind, but that's a little bit hard to explain on this one. But the idea here is that we did many studies, of course, to see how expressive those bits actually were and could they convey those emotions. And the short answer is that they could to some extent, but we actually need more than just the breathing to fully flesh out that space. But I want to move on in the story, so I'll leave it there. So that's a taste of designing the robot display. But remember I said all these other jobs that we had to work on. Sensing and recognizing affective touch was a whole nother separate line of research that we've been working on. This is one of the earliest pieces. This is Anna Flagg's work. She was a master's student a few years ago. And it's kind of fun. My favorite conference experience was Anna doing this live with a webcam at a podium at a conference. So it's always fun to say, what do you think is going on here? So what's going on here, since we don't, I can't make you raise your hands and say it because it's Zoom. What's going on here is that you have a piece of fur that has electrically conductive threads running through it. And when the threads scrabble against each other and touch them, they create different patterns of resistance. So if you imagine it's like a wire, it's like the resistance on the wire is going up and down in these crazy ways that turns out are very linked in interesting stochastic ways to the kinds of touch that you're making. And how we thought of doing this was, it was inspired by a work of Leah Buckley, who was at MIT at the time. And she posted something on Thingiverse or something, where she said, oh, look, if you use these conductive threads and scrabble together, and you kind of have a ground plane at each end, and you scrabble them together, look, it's kind of these weird signals that come out of it. And I thought, I've always wanted a fur sensor. Let's make this actually work. And so what Anna did was she made this work really, really well. And by really being very meticulous about how you see the fur and make it feel really nice, and found on different lengths of thread and all these different things, so that she could eventually make a very competent fur sensor that was extremely sensitive to different kinds of things. And then she combined it with another kind of sensor. You can tell she's a very creative person. She combined it with a fabric sensor that we were working with at the time, which is actually a conductively striped fabric put in layers, so that got the kind of the ground plane pressure, and then the fur sensor would get the little airy stuff, those little scrabbles up in the air. And then she actually did a couple papers on how to actually put that together. And Laura Kang actually started working on this stuff as well around this time. And so what that looked like, remember that touch dictionary? She took 9 of the most commonly used gestures from the touch dictionary. And you can see used machine learning on this combination of sensors. And you can see that there's kind of, here's the nine gestures on one side, and then the classification on the other side. And what you can see from the strong diagonal, if you're not used to looking at these confusion matrices, is that it was very good at distinguishing these gestures apart from each other. It had no problem. It basically got them 100% of the time. And then the interesting thing we weren't expecting with that kind of performance is it could also tell people apart. So when we had 16 participants, basically for some of the most revealing ones were Tickle and Pat there at 95-94% confidence that we could actually tell which person was making the gesture. So we could tell apart the gestures, but we could also, there was enough idiosyncrasy in it that we could tell who was making the gesture, which was pretty exciting in terms of, oh, if you have this little object, it's like you could put it into a kindergarten class, and the little object would know who was touching it from the way they're playing with it, is where that might actually go. And again, told us that we were on the right path for being able to, capture that the information was there in the signal if we could just find the right sensors for it. And then this is just a little bit of a teaser. Laura Kang, who many of you know, a current PhD student, and she's continuing to work on this. And this is a study that is going through final review right now. But we were starting to get this big concern about the way we were looking at emotions, that these static snapshots of emotions just didn't make any sense in the wild. In real life, you don't have static emotions. They're changing all the time. You're holding different emotions at once. It's not this nice controlled situation where you say, start, okay, record now, we know. Instead, they're just going on all the time. They're changing. And so we wanted to see if we could actually do better about that. And so one of the first things we needed was a more realistic environment. And to have, the first thing we're trying to attack was simply when people are giving their fake emotions. Basically, they're performing an emotion as opposed to they're really feeling the emotion. So Laura set up this Laura and Paul Bucci were working together along with a visiting PhD student, Jussi Rantala, figured out a setup where we could actually, in the lab, make a participant really, really feel something. And at least we'd be accessing the real emotion, and then we can go on from there. But before that, we had this real problem with ecological validity that we just didn't know how much our results were going to transfer over to a real situation. And so this particular model, which we developed with a collaborator in psychology, sorry, I've got a little bit of a cough, was to actually have the individual recall an emotionally powerful experience. And when saying that experience, they tell the story in private to a robot that's sitting in front of them. Again, it's not a very natural setup, but they are experiencing a real emotion, as we determined by, we had a camera fixed on their face, but no audio, so they had that privacy. And then told the experimenter, called them in when they were done. And they had very strong emotions here. It was, there were tears. It was actually the point that we felt we needed to draw a close to the experiment early, because we probably needed, maybe our ethics didn't quite cover what was actually happening in that room. It was much more strong than we had anticipated it would be. And with the data that Laura and the others collected from that experiment, we went on to really challenge this whole idea of emotion models. And we are now working with a transition-based emotion model, which very few others are actually doing, where instead of looking at these static states, we're looking at transitions from one emotion to another, and under the assumption that that is something that we might be able to detect these changes. And also they're much more realistic about what's going on. So we're not looking at absolute emotions, we're looking at transitions from one emotional state to another. And Laura and her team are currently, and Paul as well, are analyzing, doing the final analysis on a whole huge new study they did to actually pursue this idea. And we're trying to figure out how to make sense of that data. So just to move into the more forward-looking thing, there's 3 big problems which define current work in our lab. One is this accepted psychology models of emotion, static, single-valued. We're just not seeing that as being accurate or what we want to work on. And so we have a kind of position statement on this that lays that out, and we're actually now trying to document and take a different way forward with some new data that we've collected. We need better touch sensors and feature models. And actually I'm starting to collaborate with neuroscientists on this, trying to mimic human sensory organization as we try and get better at understanding how this is all working in our computational models. And then continuing with the context and get into real world context instead of the lab setups with their challenges. Nice that you can control things, but it's not authentic emotion, and it's not what we actually need to be looking at, and really understanding how, for example, our robots might be useful and helpful in actual clinical context. It's so much more than just the engineering behind them. It's also how clinicians will use them. For example, what is the mechanism? What is their mediating role? There's a huge amount of design work to go on there. And so just some highlights of kind of what's happening there. New emotion models for real-time interactivity. So these dynamic trajectory-based work, we're looking at deltas and slopes of sensors rather than absolutes, looking at how they're being expressed, how the gestures are expressed, not which gestures are being made, and looking at all these different features. So we have this idea of a topology of emotion rather than static states. And so there's just a ton of data that Laura and her student Kin Thing is working on right now, an undergrad working with her to tear through that data. I just met on that this morning. And then magic objects is what I like to call these things. This is the touch sensing side. So how do we get to these really, really richly sensitive objects that can pick up all these different emotions that all the tells you're giving through your hand? They have to be exquisitely sensitive. It doesn't have to be sensitive in the sense of super high resolution, but it needs to be able to capture a lot of different kinds of touch, stroking, pressing, pinching, rolling, shearing, all these different things that, that wonderful sensor on your trackpad of your laptop that's super precise for position, but doesn't sense anything else. Like, that's not what we're after at all. And so just picture not just fuzzy robots, but all kinds of objects that you might imagine holding that would be able to pick up your fidgets and your emotional tells, and that you could wrap that into some kind of an emotional interaction. How do we actually pick up that information? And so we've done a lot of work on pressure sensors and touch sensors. And I just want to say that there's a lot of other people are starting to work on this the last few years. One of my favorites is Jürgen Steinley's lab at the University of Saarland, where I visited a couple times. And he's doing these wonderful, sensitive things that you can, put these really sensitive things on your arms, but he's only capturing touch, not how hard. not shear, not pinching, only just, is it touching? And so I've really tried to challenge Jürgen to come up with some different models there. And then we have our own collaborator here at UBC, John Madden, just across the hall from computer science, across the alley. And he's been an inspiration to us and a collaborator, working with these gel-based polymer sensors that he can make them go and sense all kinds of different things, although not necessarily at the same time. And so we're trying to come up with different ways of doing that. And his work in particular has inspired some recent work where we're trying to make DIY, you know, stuff that you can do in your basement, especially during the pandemic, that don't require a big expensive lab like John's to actually build these. So we need highly deformable, customizable things that can sense location, pressure, shear, twist, and bend. And here's just some examples. My voice is going, so I'm going to go through this without saying too much. But 3D printing, mold making, seeding silicon with carbon fiber is one approach that we have tried. And this is actually a functioning game controller here that this crew, Hanya Shikari, Paul Bucci, worked together to make last year. And then this is another one that Anita Shaw and now Preeti Vyas are working on to make a kind of a DIY version of John Madden's work, again, making capacitance sensors out of silicon. They're super flexible, they're stretchy, and you can kind of drape them over and make them different sizes and just make them for a few dollars. And literally, Anita has been doing this in her basement over the pandemic, so they're very simple to make. And then weird soft shapes that are hard to 3D print. Another line of work. Hannah Shikari again, and also Hannah Elgabari and Paul worked on this project, which is under review at CHI right now, which is actually using origami techniques to use papercraft to make molds that you can put silicon into and make all kinds of weird shapes. And so that's a pretty fun project. And you can see we had to invent all the joinery for paper, make a tool to actually put it together, and then you can mold all this cool stuff, including even edible things from these one-time molds. And so finally, just to close, haptic robots in care contexts, this is trying to get into the real world context again. And this has really been a long, slow project. We've gotten very interfered with by the pandemic, where we have to do a co-design process with patients and caregivers. This is not something where we build robots and then kind of toss them over the wall. Develop relationships, spend a lot of time observing, understanding how the HAP technology might be workable in there, and then build new robots that will actually work in that place. So one of these environments we've spent a lot of time investing in a relationship is Connect Place, which I've already mentioned. Won't say more about that right now. It's on hold right now, as is Willow Pavilion, which is a dementia center at Vancouver Hospital, where they have a difficult, especially troubling dementia cases where they need to assess, come from all over the province and get assessed for how to care for them so that before they go home. And that this has been a place again where we were invited to come in to consider ways that we might work with them, with the robots. And then finally, as many of you have heard through our colleague Lisa Holste, there's the neonatal intensive care at BC Children's has been another environment for a kind of a non-robot version of this technology that has been fun. And I just wanted to give another nod to this, which some of you have heard a certain view of this project from the clinical side of this project from Lisa Holste. And I just want, so the idea here is putting basically turning these breathing robots inside out and putting them into the NICU underneath a new premature baby, with the idea that restoring some of these parameters that infant would be getting in the womb but has left that environment too early, that this could actually be protective for their brain health when they have to undergo painful events. And this is Lisa's research. And so it was quite an odyssey of design because there was so much going on in this environment that made it a very sensitive place when we're talking about something that could look a lot like maternal replacement, which has all kinds of difficult side effects. And so we were designing very, very carefully here to avoid triggering those kinds of results. And what was really exciting about this, you can kind of see the technology here, is that the co-design process resulted in this finding, this observation that that if the mother could be channeled into the object that breathed for the baby, breathed under the baby, rather than it could be seen as extension of her rather than as a replacement of her. This was a quite important aspect of the design in the end. And so this paper, which described this 10-year piece of design work and clinical trials, all due to Lisa's perseverance on pushing this through, got a Best of Chi award this last year, which was kind of exciting to see that all come together finally. And so that's just one of the things. This whole project has been wonderful for me because it really drew me into all these new relationships in that BC Children's environment where we're doing so much other work now. And so I just wanted to leave you with a final thought, especially I like to say this when there's a lot of students in the audience, but for all of us, is that we've identified all these ways where we think we probably are, we're inspired by trying to help, right? We're trying to do these good things. Putting a sensor-rich bot into a traumatized child's home, haptic responsive field friend that might make them actually do so much better in lots of ways when they need it. This robot is also able to listen in to everything that's going on in the house. It's a huge privacy invasion. And there's serious ethical consequences or concerns about this that have to be considered at the same time we're doing this. And as we're gearing up to do exactly this task, we also have to think about all the ways it could go wrong and how to protect that data and how to be sensitive about it. And that's equally important. We are maybe creating a surrogate environment that helps protect a vulnerable baby from future developmental issues. And so that's great. We're making something that could help these babies, but it's a slippery slope. Now, are we talking about creating technology that overworked mom or parent can now just kind of put their baby on this breathing machine to make it stop crying, when what they really need is their real mom or father to hug them? Are we creating with these care robots an excuse to not give our people the care that they actually need? So this has to be considered very closely along the same lines. And is it just a way to remove our guilt if we inject our physiology into the robot, or is it actually helping? I don't know the answers to these questions, but I think they're super important to be considering as we're doing the other things. And so we have to have balance in how we're doing the research and considering all these sides to it. And it was always hard to choose what to talk about. And so I'll just say there's all these other projects, all these other things that we're working on in the lab that I'm always love to talk about at other times. I didn't talk about physically supported learning at all, or most all the work we're doing with design tools to support haptic designers, but maybe another time that will happen, and I will stop there with huge kudos to the many, many students who have helped with this work, done this work over the years.
Great. I think we can maybe move into the Q&A session. If anyone has any questions, feel free to turn on your mic and chime in, or you could put it into the chat and we'll read them out, whatever you're most comfortable with.
Jocelyn, I have a question. It's Bill Miller.
Hi.
Really great presentation, Karon. Really appreciated that. It's an area that's held a lot of interest for me personally. I really liked how you finished off with the ethical issues, and I'm wondering if you've ever included an ethicist in your teams to actually explore that area.
I guess there's a couple ways I could answer that. One is to say, no, we have not employed someone who is would call themselves, that's the main thing they do. I think there's an increasingly an appreciation among the design community that we all need to be ethicists, that we all need to inform ourselves about the issues and work in them. But I would love to hear what, I guess I don't even know what this job description would be. I think that each situation is so individual and unusual that it's hard for one person to be expert on all of them, but perhaps I can turn that back to you. What would you recommend here?
Well, when I first left Western 20 years ago, we had an ethicist in our health sciences faculty, and really opened up the thinking in terms of considering and flipping things around, and just exactly what you did right there. So, and there are ethicists on campus who I think could do a much better job than me in terms of guiding you. But it's probably not necessary for you to do it, but it's just another avenue that's really going to be critical when we start thinking about robots and how we employ them, as you pointed out, because it could create a whole other area of guilt for caregivers because they're not there providing the essential care. Or is there a threshold in terms of the amount of care that we should be allowing the robots to take? Anyway, I'm just babbling right now, so not my area. Just that it's a fascinating thought that you ignited.
Thank you.
Thanks, Bill. It looks like Mike has his hand raised. Mike, do you want to turn off your mute and ask your question?
Yeah. Hey, very nice to hear your journey, Karon. I've of course been aware of, a small part of some of that, and it's really nice to see everything kind of in one story. Just to follow up on the ethics component, you know that my wife is, of course, runs a neuroethics research group in neurology, but one of her proteges, Julie Robillard, is actually now a prof at BCCH. And
I know Julie, yeah.
You know her, okay.
I know her. She's a DFP member at my invitation.
No, I did not know that.
Yeah.
Okay. Well, in that case, I don't have anything else further to say, but I'm glad you looped in with her, and hopefully she can be she can fill that void that Bill so rightly brought up.
Yeah, we were looking for ways to involve her more, and that's right. She would be a really good candidate for that on the robotics side in particular.
Oh, excellent.
Yeah.
Thanks, Mike. It looks like Donwook had his hand up next. Donwook, did you want to ask your question? We might skip over Donwook then and come back to him. Naz, I think you had your hand up.
Thanks, Jocelyn. Karon, that was a great talk. As a neuroscientist who studies emotions by looking at brain signals, I'm just wondering about whether you've looked at the correlation between the touch sensing and the signals that are coming from the brain with different emotions, because not everybody will express their emotions necessarily through the way that they're touching. They may also be lots of cultural differences in how people express touch and what they're actually, what their brain signals are showing in terms of specific emotional responses. I know you started some EEG work, and I just wondered if you'd looked at that correlation at all.
Yeah, and you're on, by the way, Naz, you're on our list of people that we want to puzzle over our data with you, actually, for exactly that reason, because we're relatively new to the EEG part of it, and coming up the curve on that, it's a new tool for us. So yes, we expect there to be huge individual differences. Cultural is actually not one that I had thought of, though, but there's plenty without that. We are learning how to use this tool and how to connect it. Collecting the data is a huge challenge. Trying to, I said a little bit about the challenges of actually getting genuine felt emotion, and Laura and Paul developed this whole protocol for using an immersive video game, and just trying to sort of, there's two separate problems. One is setting up the generating the emotions, situations in which they can have the live emotions, and then the second one is now give them something to do with their hands at the same time, so that we can actually collect the manual data. And so we're kind of picking off one at a time, and we're looking first at the can we actually see it coming through at all in the expressive things? And then secondly, we're going to be going after the more expressive touch part. It's a long journey for us, and we'd love to talk to experts like you about it to come up to speed faster on it.
Great, would love to talk to you. Thanks, Karon.
That's great. You'll be hearing from us probably pretty soon, actually.
Okay.
Thanks, Naz. I think our next person is Katra, and I'm pretty sure Katra is one of our new DFP cohort 4 students. So welcome, Katra, to the Create.
Hi, Katra.
Hi, Karon. Yeah, thank you very much. This was a great presentation, and thank you for your your ending where you talked about privacy. The only thing that I worried about it after you brought it up is for those vulnerable moms who the medical system thinks they could be able to replace them and say, you're not needed, and they'd be able to lose access to their kids, that they'll say this might be a replacement to them. Or what would worry me. And I don't know if this is something you've looked at or thought about.
Yeah, I'm that's just one of many scenarios that we've had some concerns, and Lisa Holste, who's here with us, might have some thoughts on that as well. It's a really difficult problem. Because definitely this work was initially focused on a particular group of vulnerable children who everyone agrees it would be better for them to be with their real mom, and that is just not available to them in these circumstances. And so we're trying to solve that problem. But this technology, we would expect, would have some degree of beneficial effect, not clinically proven at this point, but reasonable to expect that it would also be helpful for other kids who are not in such dire straits, but their families might have very severe constraints on them, and they might have non-health reasons for wanting assistance. And is that okay? You know, and I think there are many people on this call who have had the experience of having young children while they've got a lot else on their plate. And the temptation to, I see Joanna, okay, you're right there. The temptation is huge to take the assistance where you can find it. And so are we enabling that, and how can you reduce it? Now you brought up another really challenging case of, you know, where it actually could break apart a family. And I would hope that would be something where policies and regulations should be cultivated at the same rate that the technology becomes available. Like, it's not something that should be waited for. You're not waiting for the problem to come up before you start being proactive about it. And I think that that's one of the big things that the tech community in general is not got a great track record of, is anticipating some of these big problems before they happen and guarding against them, because once the cat gets out of the bag, it's much harder to put it back in. So thanks for, you know, it's our job to try and raise all those ways it might go. I should also say that this is just an example. The place where the idea of robot technology, social care robots being problematic, has gotten much more traction, much more discussion, of course, is in senior care. And, you know, where you have a situation where the demographics are just really working against us, and especially in some countries. And yeah, you can see lots of discussion about it, but I think not a lot of resolution about how to solve these problems.
Thanks, Katra. We've got 2 more questions lined up, but I wonder, Karon, you mentioned asking if Lisa wanted a chance to respond to that question as well.
Yeah, thanks, Katra, for the really good question. I would just say that with respect to the Calmer, it is being designed and used in a very specific context. And the thing that Karon mentioned is that when we get to the stage where it is more broadly implemented, along with it are going to go very clear clinical protocols about when it's to be used. So we're not at that stage yet, but I agree with Karon 100%. That's the approach we will take, and that we're not in the business of just distributing without very clear guidelines and principles around having it being used. And nurseries are very used to that sort of thing, that there are clinical protocols and decision trees and all of that kind of stuff. They're very used to that kind of documentation, so it's not foreign to them that with another piece of equipment in a high equipment environment that there would be specific protocols about it.
Perfect, thanks, Lisa. Bonnie Barrett has a question. She's asked in the chat, are you currently collaborating with anyone in mental health or autism?
Yes, not autism. It's been difficult to find the right partners. I'll just kind of a general life lesson for me as a researcher has been that collaborating with clinicians, there's many different kinds of clinicians. Not all of them like to do research, and kind of the perfect clinical collaborator is, we call it a clinician scientist who does both. And then you have to find, when you're the kind of the technology person saying, I think I have something that could help here, I need a clinical partner to move that idea forward. And the clinical partner needs to think this is so exciting to work on that they will stop doing something else they're doing in order to work on this idea with me, as opposed to a clinical partner coming to, say, me or, you know, your generic technology person and saying, could you help me build a thing like this, which is more what Lisa did, I think, with the calmer idea. And so it can be very challenging to find the right partners, you know, where the magic happens and you both are excited about the same thing and have the kind of the capabilities and the research mandate in your professional life. And I have not been able to find that in autism, although there must have been 100 parents who have asked me to please somehow find a way to do this with autism. I'm not an autism expert myself. So not autism. Other kinds of mental health definitely have been working with a number of people over the last 15 years, mostly in BC Children's, mostly oriented towards kids, but there's also a lot of ideas of working with chronic pain, as well as anxiety management is the big one in cognitive behavioral therapy. And we've really, over the last 5 years, have been focusing on trying to get the technology up to the point where we can do that. And then, of course, the places we're talking at Canuck Place and Willow Grove, that those are really about, those are primarily going to be mental health interventions with individuals with complex situations that they're working with. And part of the challenge here is not just, you know, giving a pill to someone, or I'm saying that in a metaphorical way, you know, delivering a treatment. It's actually how you work with the clinical caregiver team. You have this new tool. How does the team deploy that? You know, how does it work? And this gets back all to this idea of replacement. We've never been trying to build robots that replace anyone, but the models that we're looking at, for example, in those two environments are how can the object be an adjunct? How can we design an object that's an adjunct to the care that is being given, that is perhaps something that's diffusing a challenging situation. There's some situations, for example, where there's violence involved in the dementia cases, and perhaps having a relationship with this object would be something that could work, where you have a triangle. Now you have the patient, you have the caregiver, and you have the object, and you can actually do different things now with that triangle than you could with just the pair. Those are some of the ideas that have come out of the caregivers that we've talked to there. So I just want to emphasize that a lot of the design here is how you deploy and then design a thing that works in that kind of deployment and see how it works. And that's really what the research is looking like.
All right, we have another question. This one's from Tibor, who is actually one of our new DFP affiliate members. So welcome, Tibor.
Thank you. Thank you very much. First of all, Karon, I want to say your talk is like the quintessential for me, why science is cool. I'm just like, I just like when science is cool. This is just so great to see this. And so my question is maybe a little bit out there, and it's a bit further from this research, but I was struck by the idea that we're all sitting here looking at Zoom, and I wondered if we could use this robot technology to have two of these pets and make a connection between two people where, you know, we're very often sitting on the couch here and petting the same pet, and could we do that in a distance way, and would that create more of a bond for people?
Yeah, this idea has come up a lot of times, but I've never seen it really done convincingly. Not just by me or my students either. I've seen it kind of shows up in papers now and then. People do it often with like a handheld object that is sort of reflecting what the other person feels. So you sort of have this shared object. And there are a lot, when you start thinking about how it would work, and not surprisingly, there's tons of questions and all kinds of things you hadn't thought of that make you wonder. But I'm not sure I've ever seen or heard of a really convincing demonstration of someone really trying hard to make it work. So I'm not saying it wouldn't work. I'm rather saying I don't think it's really been given a fair chance. So I'm kind of waiting for maybe a student to come along and say that's what they want to try doing. I think it's very interesting. And it could be a very pandemic relevant.
Yeah, that's what I was thinking.
Yeah, for sure.
Thank you. Thank you for the talk.
I hope all the students are listening.
Okay, I think that is all of our questions for now. But I imagine, and correct me if I'm wrong, Karon, if people have more questions, they could maybe reach out to you.
Yeah, and we should let people go on to their next, if they haven't already, go on to their next Zoom meeting. But thank you so much. This is what I love about DFP, is all the great conversations and people that I get to follow up with on it afterwards. Thank you.
Thank you everyone for attending, and we will see you on December 9th for our next seminar.